start my seminar by extending my sincere thanks to Dr. C. Veerababu, the principal of Vivo Sidambaram College, and also the president of this webinar series. It is because of his support such successful activities can take place. And thank you very much for your efforts, sir, in catering the students in this hardship time. And I'm very happy to see the growth of the college. Over the time, it has reached greater heights. And I'm sure that in the days to come, VOC College will top as one of the best college around in southern part of Tamil Nadu.
Thank you, sir. Thank you very much for your blessings.
Yeah, I'm sure that you will reach NIRF ranking above,
Yes.
I mean, top 50 or top 25 in the coming years, because such events are taken as a parameter to measure the strength of the college, and the activities by the Department of Physics, like solar installation of solar plants and other activities to the society, definitely will have a great impact in evaluation parameters. And I'm sure that I want to see this college at the top position in the days to come.
Thanks.
Thank
you, sir.
And I would like to thank the convener, Mr. T. Murali Narayanan, Head Department of Physics, VOC College, and the organizers, Dr. John Prince, the man behind coordinating this webinar event, as mentioned by Dr. Veerababu sir, for the last 1.5 months, engaging students during this hardship time, because the students are engaged, and I'm very happy that Dr. John Prince takes a lot of sincere efforts in coordinating such meetings, not only to physics. I think he's arranging for all disciplines. So I extend my personal thanks to Dr. John Prince and the co-organizer, Mr. S. Subramanian, and above all, to all the participants of this seminar or webinar who attend this from various places across our state and different institutions. So with this small introductory note, I will proceed with my presentation. So as was introduced by Dr. Infanda, so I am Dr. M. Balasubramaniam, working as a professor at the Department of Physics, Bharathiar University. And I would like the participants to note down my email ID so that you can post your comments or questions if you could not raise today, or if you do not get an opportunity today. So you can always post your comments and questions to my email ID. So it is mbs.phy@gmail.com. And also, the title of my webinar today is History of Nuclear Fission. So this is a very broader title, and I'm not sure whether it would be possible to cover the complete history behind nuclear fission. Rather, I would like to touch upon some of the important incidents and the happenings happened during the discovery of nuclear fission. So this seminar or webinar is not about a physics lesson, and I'm not going to discuss the physics of nuclear fission. Then obviously a question would arise in your mind that what you can expect from this seminar. So this seminar may give you a better understanding of how science is done, and this seminar would give glimpses about the scientific processes, and this seminar would address about the lives of some renowned individuals who were involved in that processes, further their role in solving a particular problem. So in a nutshell, in this seminar, I will mention about the frustrations faced by the scientists, their successes, their prejudices, and about their worldview. So the plan of this seminar is as follows. So in the first part of the seminar, I will give an overview about the evolution of fundamental building blocks. And then in the later part of the second half of the seminar, I will discuss about the discovery of nuclear fission. So in ancient times, the Greek philosophers, they do Gedanken experiments. That means they do thought experiments. So they don't have access to modern day equipments or laboratories. So what they do is simply thought experiments. They see, they think, and they talk about what they observe in day-to-day life. And always they try to find answer to a fundamental thing that persists through the constant change. And one such hypothesis was put forth by one of the Greek philosopher whom we regard as father of modern science and who is none other than Democritus. So the period is between 460 to 370 BC, and he is remembered for his atomic theory and his hypothesis. According to his hypothesis, everything is composed of atoms, and atoms are physically indivisible. And between atoms, there lies empty space, and further, atoms are indestructible. So these were the ideas put forth by Democritus, and unfortunately, his ideas and thoughts were not appreciated by his fellow colleagues. So he wanted to burn all of his works. He wanted to burn all his books. And in Sangam literature period, during first and second century of CE, we have some references to the word Anu. Tamil, just I want to make a reference in Tamil. Avvaiyar has stated in appreciation of the work by Thiruvalluvar the following lines. அணுவை பிளந்து ஆள் கடலை புகட்டி குறுக தரித்த குரல். ஸோ இதில் அணு அப்படிங்கிற வேர்ட் வந்து இட் ரெஃபர்ஸ் டு சம்திங் வெரி ஸ்மால். ஸோ எதர் டெமோக்ரட்டிஸ் ஆர் அவ்வையார் may not know what exactly we mean atom today, but they have used such concepts in those period. So அணுவை பிளந்து means something very small, and if you break that and if you put information of 7 C's, so that is equivalent to the recitation made by Thiruvalluvar in 1.5 lines. So the 1.5 line of Thirukural contains information equivalent to 7 C's, that is the meaning. So such references to the words like Anu appears in different literatures, and I'm very happy to show you that our language Tamil has a very strong vocabulary for referring to these numbers. For example, we are very much familiar with the numbers like ஒன்று, முக்கால், அரை, கால். அதுக்கப்புறம் பார்த்தீங்கன்னா பின்னாடி வரக்கூடிய ஃப்ராக்ஷன்ஸ் we may not be aware of. Maybe we know one or two. For example, here in Tamil there is a word called immi. Immi அளவு அப்படின்னு நம்ம colloquially யூஸ் பண்ணுவோம். So that refers to the order of 10 power minus 7. And similarly, you could see the word anu is referred to a number equivalent to 10 power minus 9. So closer to what we know scientifically today. And apart from these different words, there are other words which is being used in day-to-day life, like L. L எல்லாருக்குமே தெரியும். So it is small in size or millimeter size. So L அளவு அப்படின்னு சொல்லி தமிழ்ல நம்ம சொல்லுவோம். அதுக்கும் சின்ன அளவு வந்து அல் அப்படின்னு சொல்லி தமிழ்ல ஒரு வேர்டு இருக்கு. அல்பம் அல்லது அற்பம் அப்படின்னு சொல்லுவாங்க. அற்ப புத்திக்காரங்க, சின்ன புத்திக்காரங்க. So those people who do not have butti, they don't have a butti. That means they have very small butti. And அதுக்கு கீழே பாத்தீங்கன்னா அன் அப்படின்னு சொல்லி ஒரு வேர்டு இருக்கு. So that refers to anu, that is very small. So they have some relative scales denoting various sizes, and they may not know the exact scientific understanding of what an atom is, but such scales existed in olden days, different literatures across the world. So the scientific evidences started to come in the years 1600 onwards, when scientific instruments began to be invented. And we can credit Robert Boyle as a person who stated that matter was comprised of small particles and not the 4 elements. And then later in 1808, John Dalton performed a series of experiments and determined the atomic weights of various elements, and he is best known for introducing the atomic theory. And according to John Dalton's atomic theory, elements are made of extremely small particles called atoms, and for a given element, atoms are identical in size and mass, and atoms cannot be subdivided, and atoms of different elements combine in whole number ratios to form chemical compounds. So according to Dalton's theory, suppose if we have one oxygen atom with 16 mass units, if it combines with 2 hydrogen atoms of 1 mass unit, that will give a water molecule with 18 mass units. So till the time of Dalton, it is considered that atoms doesn't have any internal structure, that it cannot be subdivided, and atoms are the fundamental building blocks. So in 1815, another chemist, William Prout, put forth a hypothesis based on his observations about atomic weights of various elements, that all atoms are composed of hydrogen atoms, and he referred that as protyle, Protylle. And he further hypothesized that hydrogen atom was the fundamental object which makes all the element, though it is not a scientifically verified fact, but it was one of the important hypotheses put forth by this scientist, William Prout, in the year 1815. So, if you still come forward, 1869, so we know this gentleman with sporting a large beard and wearing a heavy woolen coat. So, he is known to us since our school days. So, he is Dmitry Mendeleev, and last year, UNESCO, that is United Nations Educational, Scientific and Cultural Organization, celebrated that year as International Year of the Periodic Table of Chemical Elements, marking the 150th anniversary of Mendeleev's periodic table. And this is the handwritten notes or hand-drawn notes of Dmitry Mendeleev about the periodic table. You could see that it was written on 1869, February 17th. And the equivalent typesetted version is shown alongside, and you could see that there are empty spaces and question marks, so which were not understood by them at that time, which were later filled with modern day discoveries and inventions. So till this period, the concept was only based on atomic weights and atom as a fundamental unit. So the internal structure about atom was not established till 1869. Though it was not experimentally verified fact, the internal structure of an atom, the following questions remained in the minds of the mankind for quite longer time. What are those questions? The questions are: can atoms be split apart? Is it possible to break an atom? Does each atom have inner workings? Is there any possibility to have or to study internal motion of an atom? Or is it possible that the parts of which can be separated? Or is it possible that parts of which can perhaps be put to some use? So these questions remained in the minds for quite some time, quite a longer period. And these questions were answered when J.J. Thomson isolated the electron in 1897. So that experiment was the first solid proof that atoms are indeed built of much tinier pieces. So they have demonstrated that atom indeed has internal structure containing electrons. So in 1897, J.J. Thomson, during the investigations of cathode rays, discovered electron, and he initially referred them as corpuscles, and his discovery played a pivotal role in understanding the atomic structure. So the ideas of J.J. Thomson were refined by one of his finest students, the scientist which I like the most, Ernest Rutherford. So Ernest Rutherford, he demonstrated or he showed that mass in an atom is not smeared out uniformly, rather it is concentrated in a tiny inner kernel called as the nucleus. So he has published such findings in the year 1911. So this result confirmed the presence of a nucleus inside the atom. The title of his research paper reads as "The Scattering of Alpha and Beta Particles by Matter and the Structure of Atom," published in the research journal Philosophical Magazine in the year 1911. So this is one of the classical experiment ever done in the history of science. This is the gold foil experiment, which confirmed the presence of a nucleus inside the atom. So we have the thin gold foil placed here, and the radioactive sample which emits alpha particle is allowed to bombard on this gold foil, and simply we observe the scattered events through this zinc screen. So it is seen that some of the particles passed undeflected, passing the target, and some deviated with some angle, and certain alpha particles bounced back towards the direction of the beam. So indicating that there is something massive entity present inside the atom, which deflects back the incoming alpha particles to backward angles. So this is the Thomson model, and according to it, the electrons are assumed to be embedded inside the atom, whereas in the Rutherford model, it is proposed that there exists some massive entity at the center of the atom. So not only he stopped with the discovery of the nucleus of an atom, but he continued his experiments, and in 1917 he reported that the hydrogen nucleus is present in other nuclei, a result usually described as the discovery of the proton. So he was inspired by the works of William Prout, and he performed several experiments, and in one such experiment he observed the proton as an outcoming particle, and he named this new fundamental particle as proton, the neuter singular word for first. Initially, he suggested two names. One is proton and the other one is proton. So this word is proposed by him to honor the work of William Prout. However, the word proton remained in the literature in the following years, and the official use of this word proton in the scientific literature appeared in 1920. So, though the experiment was performed in 1917, this was published in the journal Philosophical Magazine in the year 1990. In this experiment, the interpretation put forth by Rutherford and his co-workers was something like this, but the actual experiment is shown here. So 14 nitrogen alpha P reaction, 17 oxygen. That means alpha particles from a radioactive source is allowed to bombard on 14 nitrogen, resulting in the emission of proton along with 17 oxygen as the daughter product. However, the interpretation published in the paper by Rutherford and his co-worker is something like this. So I just read those statements as it was published in the paper. The long-range atoms arising from the collision of alpha particles with nitrogen are not nitrogen atoms, but probably charged atoms of hydrogen or atoms of mass 2. So this was their interpretation. And they further say, if this be the case, we must conclude that the nitrogen atom is disintegrated under the intense forces developed in close collision with a swift alpha particle, and that the hydrogen atom which is liberated formed a constituent part of the nitrogen nucleus. So this was their interpretation about the outcome of this experiment, and they suggest in a notation something like this, that 14 nitrogen is a target and 4 helium is the projectile coming out of or emanating from a radioactive source, which disintegrates into 13 carbon plus 4 helium plus 1 H. So, but actually, this is not the case. What they have observed is really 17 oxygen. So, this experiment was later redone and confirmed by one of his student, Patrick Blackett, and was published in the year 1925. However, this reaction is treated as the reaction which discovered the entity proton, which makes as the fundamental entity of the nucleus. And you could see that this is the lab setup used by Rutherford and his students for performing the first ever experiment for making artificial transmutation of the elements. And this is another important experiment performed by co-workers of Rutherford, Cockcroft, and Walton. So you all may know that it is P alpha reaction where the target is 7 lithium and the product is another alpha particle 4 helium. So this is a very historically important reaction for the reason that where the protons were fired from a voltage multiplier, the olden day accelerators, as bullets into the targets. So before the Cockcroft-Walton experiments, the projectiles were mostly used from the radioactive sources available at that time, mostly alpha particles. And this is the first experiment where they have demonstrated that it is possible to accelerate particles and allow them to interact with the target. And as a result of this experiment, the collisions transformed some of the nuclei in the targets, and some of the atoms' mass was converted into energy. And this experiment, for the first time, proved Einstein's concept of mass energy relation. So immediately after the publication of their results in the year 1932, there were news reports in newspapers stating that scientists had shown that innermost entity of an atom, if smashed, yields tremendous amount of energy. Not only the conversion of 7 lithium into byproduct of alpha and alpha, but there is amount of energy is also released that has been speculated in various newspapers at that time. However, this is not the case. The energy released is very feeble than the energy they have invested in performing this reaction. So this happened in the year 1932, and in the same year, there was another important experiment changed the way we understand about the atomic structure. This is 9 beryllium alpha N reaction producing 12 carbon and neutrons. So alpha particles are the projectiles which emanate from radioactive source, which are allowed to bombard on 9 beryllium, resulting in the emission of neutrons. So this was performed by James Chadwick in the year 1932, and his results were published in the journal Nature during 27th February 1932. And he says that he observed particles which have a mass about the same as that of the proton, but has no electric charge. So due to this peculiar property, it opened up various avenues for further investigations in the field of nuclear physics. So now we have come to some stage by 1932 that atom indeed is not the fundamental building block which makes up the matter. Rather, atom has internal structure, as was first discovered the electrons and then the nucleus and then the inner constituents of the nucleus. So we know that now atom is no longer the fundamental building block, and it has internal structure, it has internal motion, and so on and so forth. So we have illustrative diagram indicating its sizes and the energy units. So atom is of the order of 10 power minus 10 meter in size, and at the central part of an atom lies the nucleus. The size of the nucleus is of the order of about 10 power minus 14 meters. We refer it to as femtometer or Fermi. And then we have internal constituents of the nucleus called as nucleons, protons, and neutrons. And in turn, later it was shown that protons and neutrons are also further made up of particles called quarks. So let me just show the composition of the nucleus, taking an illustration of 4 helium. So this is a 4 helium atom. So you could see 2 electrons orbiting in the outer shells, and inside the center of the atom we have the nucleus consisting of 4 nucleons, 2 of which are proton and 2 are neutrons. And these protons and neutrons are in turn made up of quarks with a combination of UUD making protons and DDU making neutrons. So this combination of UUD having a fractional charge of 2/3 and minus 1/3 gives a total electric charge of 1 to proton and gives electric charge of 0 to neutron. And of course, electron has no internal structure, and as is quarks. Quarks also doesn't have any internal structure, and our understanding still have the question whether electrons and quarks will have internal structure or not. Just to imagine the size of an atom, we can scale it up, and in a scale model, if you assume if each proton were 10 centimeter across, then each quark would be 0.1 millimeter in size, and the whole atom would be 10 kilometer wide. So you could imagine how small it is. So let me define another term that is called isotopes. So we all know that isotopes are variations of chemical elements that have the same number of protons but a different number of neutrons. For example, I have just illustrated here 12 carbon atom has 6 protons and 6 neutrons. And if you add up a neutron, this becomes 13 carbon. The mass number gets changed and number of neutron gets increased by 1. So likewise, we have same element with a different mass number. We refer to them as isotopes. And this picture gives the nuclear chart we know as of today. So as of today, we know about roughly 3,500 nuclides, and each small boxes in this chart refers to one individual nuclide, and the black boxes are stable nucleides. So they are stable, they will not disintegrate spontaneously. And other colored boxes are radioactive or unstable nuclides. For example, these green ones lying below the black boxes are beta minus emitters. So these nuclei will emit beta minus particle, and finally it would attain stability and reach these black boxes. Likewise, these pink squares are beta plus emitters. So this also will emit beta plus particle to reach down to this stable nuclei. So if you go higher in the mass numbers, you could see other colors appearing, yellow boxes and then green boxes. So these yellow boxes are alpha emitters. So these nucleides spontaneously would disintegrate, emitting alpha particles. And the green ones are the nucleides which spontaneously break into two, resulting in spontaneous fission. So we all know that any heavy parent radioactive nucleus would disintegrate by emitting different particles. We study right from the school days these fundamental decay modes. Alpha decay mode, where a parent nucleus results in the emission of alpha particle along with a daughter product, or it may emit a beta particle along with the daughter product with no change in mass number and additional neutrinos. And then a parent nuclei in its excited state may emit a gamma photon reaching to its ground state. And sometimes spontaneously a radioactive nucleus can disintegrate into two equal halves, a process we call it as fission. So these are all known decay modes for quite some time. Apart from these known decay modes, there are other exotic decay modes which are recently being investigated and studied. And one such decay mode is called as cluster decay, where heavy clusters, heavier than alpha particle, are emitted like carbon, oxygen, and so on and so forth. And then at some time, the parent nucleus may disintegrate into three fragments, a process known as ternary fission. And sometime at the extreme ends of the nuclear chart, at the boundaries due to excess neutrons and protons, a parent nucleus can either expel a proton or neutron, a process we denote it as proton emission or neutron emission. So we are going to see now only on the aspect of fission, and particularly the induced fission and how it was discovered by the great scientists involved in that process. So as I have mentioned earlier, after the experiment by Cockcroft and Walton bombarding proton and lithium, so there were speculations in the newspaper about the amount of energy released during those experiments. However, one of the famous scientists, Rutherford, he is of having different opinion, and according to him, these transformations of the atom are of extraordinary interest to scientists, and but we cannot control atomic energy to an extent which would be of any value commercially. And he says that I believe we are not likely ever to be able to do so. So, according to him, the energy released in a nuclear reaction is having interest only for scientific purpose, not to any practical use. That was his intention. However, his fellow scientist at that time, Leo Szilard, he thought of a possible way to find some sort of nucleus that would emit two neutrons. So we bombard a target nucleus with a neutron, and as outcome of the reaction, if two neutrons are emitted, then we can sustain a chain reaction. So that was the first idea put forth by Leo Szilard. Unfortunately, he doesn't have any funding to perform his experiment and to confirm his ideas. So after the invention of neutrons by Chadwick, several groups across the world started using neutron as a beam to investigate, to find or to synthesize new transuranic elements across the globe. And one such group, headed by Otto Hahn in Germany, there were two German chemists, Otto Hahn and Fritz Strassmann. So they began to focus their attention on uranium, the heaviest of known elements at that time. So they wanted to bombard a neutron on uranium and to see an outcome which is heavier than uranium. That was their idea. So along with them, Otto Hahn and Fritz Strassmann, Professor Meitner worked in their lab, and she was a collaborator of Hahn's laboratory. She had to leave Germany due to World War situation, and she left the laboratory on July 1938, and she went to Sweden. So this happened during July 1938. So after July 1938, Strassman and Hahn, they had to work alone again, and in the atom of 1938, they found some strange results. So you just remember the period. So July 1938, Professor Meitner leaves the lab of Hahn and she proceeds to Sweden. And Strassman and Hahn started to work alone without the help of Meitner. And in the atom of 1938, they found some strange results. So, what are those results? So, actually, they were trying to find out what products are formed if you shoot neutrons into heavy elements. They hoped to find elements even heavier than uranium. So here I have shown a small part of the periodic table. You could see that in actinide series, we have heavy elements starting with atomic number 89, 90, and so on and so forth. So we have uranium with atomic number 92 here. So this uranium is bombarded with neutrons, and they wanted to look beyond uranium. However, the substances they obtained out of the outcome of this experiment looked like radium or barium. So you see, uranium is here, radium is here, and barium is here. So two unknowns, two known and almost chemically identical. They have chemically similar properties, barium and the radium. So their expectation was to find an element heavier than uranium, but the outcome of the experiment indicated that they have something similar to radium or barium. So they didn't dare to think it as barium in those times. So அவங்களுடைய மைண்ட்ல they are not able to uh, polarize their mind to accept their outcome as barium for two reasons. One reason is that physicists of that time did not suppose a heavy element like uranium could be transformed into a light element like barium. So they were afraid that physicists may not agree about the outcome of their experiment, because you might be able to knock off four protons from the nucleus of the uranium atom and create radium. Suppose if you bombard a neutron, it may be possible that four neutrons can be chipped off from uranium that may result in radium. However, if it were barium, the neutron has to chip off 100 particles. So physicists may not agree with the results. This was their opinion, and based on this opinion, they were afraid of physicists, and they always tried to explain what is wrong in their experiments. Not to say they do have barium as an outcome, but they always thought it cannot be there, and therefore we have to say what is the nonsense we are doing. So they were really not able to convince their mind about the outcome of that experiment, because they were afraid of the physics people of that time. And this is the working lab and the working table of Hahn and Strassman. And this setup is still preserved in Germany. And you could see the preserved working table of Hahn Strassman. This is the table in which the first fission experiments were performed by Otto Hahn and Strassman. So, in the second week of December, let us say, Hahn wrote to Meitner, Lise Meitner, describing the strange results they obtained. And after receiving the letter from Hahn, looking at it, Meitner was also very much surprised. So, during that month, at the end of the month, during Christmas period, Lise Meitner's nephew, Otto Frisch, visited her for Christmas. So, he worked as a physicist at the Niels Bohr's famous institute for theoretical physics in Denmark. So from Denmark, he visited her aunt, Lise Meitner, at Sweden. And Lise Meitner conveyed the results of Hahn and Strassman to Otto Frisch, and they started discussing about the results. And as an outcome of their discussion, Lise Meitner drew a shape something like this, a circle, and then there is a circle inside, a dotted circle. And she was asking Frisch, is it something like this? Then Frisch realized that what she intended to say, so he drew a shape something like this. So that is pushing a spherical shape at the center, resulting in two lobes. So this is seen in a lateral view, and this is what Frisch has perceived in his mind. And after immediately seeing this, Meitner appreciated the views of Frisch and said this is what exactly it has to be. So they interpreted the results that after the bombardment of neutron, uranium just breaks into two lobes, resulting in barium and counterpart fragments. So they agreed that they should write a paper about the interpretation. So this happened just during the Christmas time in 1938. So immediately after Christmas, in a couple of days, Otto Frisch left to Denmark from Sweden, and from Denmark he started writing a research paper as an outcome of the discussion with Lise Meitner, and he used to convey to Lise Meitner over phone about the draft version of his paper, and Lise Meitner corrects from the other end through phone, and this was kind of a costly, expensive way of writing a research paper, as was remarked by him at a later time. And in addition to the discussions made with Lise Meitner, Otto Frisch decided to make an independent confirmation. So he's not satisfied with the discussion with Meitner, but he wanted to convince himself by doing an independent confirmation, and he simply devised the experiment after returning from Sweden to Copenhagen. So when he reached Copenhagen, he found Bohr just on the point of leaving for America. So Niels Bohr was about to leave to America, to Washington, for attending a theoretical conference to be held sometime in January. And he told him that what Lise Meitner conveyed to him about the results of Hahn and Strassmann. And Bohr was looking at the papers presented to him by Otto Frisch, and Bohr was very excited, and he said, "This is exactly as it must be." And he added that this is very beautiful. So after Bohr left, Otto Frisch reached the lab. So he wanted to do some independent confirmation of what Hahn and Strassmann has observed. So the easiest way to identify fission is through electrical effects. So we know that if invisible particles, charged particles, if it passes through a chamber, ionization chamber, that would show it up as pulses on the screen of the oscilloscope. If the emitted fragments were very large, possessing large charge atomic number, the pulses would be very large. So this is the simplest idea. So immediately he devised the setup in 2 days, and he got the results at 3 a.m. in the morning. So he has made the first independent confirmation of nuclear fission during the last weeks of December 1938. So the papers, as decided with Meitner, were written, and he wrote his independent paper, and both of these works were sent to the journal Nature at the same day. But the journal Nature published one after the other, and he still remembers that the word fission occurs in the first paper, and it was suggested by him to Lise Meitner through his American biologist friend William Arnold, whom I asked, that means whom Frisch asked, that what do you call it when a cell divides itself? So this word was borrowed from a biologist. The word fission was followed from a biologist. So in the meantime, Bohr traveled to USA, United States of America, and he came to Columbia, and he was received at the port by Enrico Fermi. And the next day, Bohr went to Columbia University to discuss with Enrico Fermi. At that time, Fermi was not available in the lab, and one of his graduate students by the name Anderson, he was around, and Bohr was very curious to convey what he had just learned from Otto Frisch. And Bohr tells to Anderson that that there is some experiments performed by two chemists in Germany about fission. So after Bohr left the lab, Anderson finds Fermi in his office, and he discusses with Fermi about this and realizes its excitement and importance. And Anderson was a very curious young undergraduate student, and Fermi was the boss. And immediately he wanted to do some confirmation experiments. But the next day, Fermi, along with Bohr, left to Washington for attending a theoretical physics meeting, and Anderson was left alone in the lab. And there was another professor by name Dunning, and they decided that let us try this new experiment, which was conveyed to them by Bohr. So Dunning, though a senior professor, so he went up to the 13th floor of that building, and he brought down one of the old standard standby neutron sources, a source called the radon plus beryllium source that had been used earlier before very much. And they put that source next to the ionization chamber containing the uranium. And in considerable excitement, they saw with even this very weak source a one big pulse, a huge pulse on the oscilloscope every minute. So it's a very simple experiment. Everybody can do it, provided if you have access to a neutron source. That is a difficult part of this experiment. So if you have even a weak source, that is sufficient, and the rest of the thing is we just make some uranium target and put it in the ionization chamber, allow the neutrons to bombard on the target, and you could see in the outcome as a big pulse. However, the rate, since the source was used for quite long time, the intensity of the beam is very low, and hence the rate of reaction is also very low. But they have independently confirmed the fission event again after Frisch. So meanwhile, Bohr and Fermi were attending the meeting at Washington, and one of the closest associate of Bohr at that time was John Wheeler, and Bohr wanted to convey to him about the fission findings. However, he owed it as a responsibility to Frisch and Meitner that word of their work in progress and their concept should not really be released until they had the proper scientific opportunity to publish it. So Bohr just conveyed the glimpses about the outcome of Hahn-Strassmann experiments without narrating it too much. But however, the second day of the conference, the issue of the Nature Wissenschaften arrived at Washington, and it was handed to him, and which has just come in and which had the work of Hahn and Strassmann. So this happened sometime in January first week. The work of Hans Strassmann was published during January first week, and the paper reached the United States, say sometime in the second week of January. And once it is published, people were very excited about fission and the associated energy involved in that reaction. So I just give another important and hilarious account by one of the famous scientists by name Alvarez. So Alvarez is a leading experimental nuclear physicist of that time. He was sitting in a saloon having his haircut, and he was reading the newspaper Chronicle. And in that paper, a small news item, it was mentioned that German chemists had found that the uranium atom split into pieces when it was bombarded with neutrons. So immediately after reading that news in the newspaper, Alvarez remembered that he asked the barber to stop his haircutting, and he rushed to the lab because one of his students, Phil Abelson, he was working on bombardment of neutrons on trans uranium to find the trans uranium elements. And Alvarez quickly realized that they were very close to discovering fission, but unfortunately, it was already reported by Hahn and Strassmann. And Phil Abelson was very much depressed hearing the news from his mentor Alvarez. In the meantime, the first report or the first paper on nuclear fission was published in the journal Nature Wissenschaften. And the title of this reads as Deduction and Characteristics of Alkaline Earth Metals Formed by Irradiation of Uranium with the Neutrons, with the authors as Otto Hahn and Strassmann in 1939. This was published in volume 27 of first issue and dated 6th January 1939. So, and simultaneously, Lise Meitner and Frisch started to understand the strange results of Hahn and Strassmann. They write an independent paper on their discussion, and Frisch independently confirms nuclear fission through physical experiments. And it happened very quickly, right from December to January. January 6th, the work of Hans Strassmann got published. In the meantime, after the issue of Hans Strassmann reached one of the laboratories in France where Juliet Curies were working on 16th of January, they were very happy to see the results of Hans Strassmann. And one of his co-worker, Dr. Kowarski, he states that Juliet Curie probably had his first glimpse of Hahn and Strassmann article in my presence, and it was, of course, a bombshell to them. So immediately, the Paris group, led by Juliet and Irene Curie, they decided to do some independent experiment to confirm fission. But at that time, it is during 16th January or during the third week of January, they were not aware of the results of Frisch and Lise Meitner. But the thing is that immediately within a couple of days, they made an independent confirmation. So immediately after knowing the results of Hans Strachman when it was published in a journal, several groups across the world reconfirmed the experiments through various means, either through chemical means or through physical means. So the paper of Lise Meitner and Frisch, titled "Disintegration of Uranium by Neutrons: A New Type of Nuclear Reaction," was published on 11th February 1939. And in the next issue, I mean, in the same volume, the next issue, the independent paper written by Frisch was published, entitled as "Physical Evidence for the Division of Heavy Nuclei Under Neutron Bombardment." So these papers are the hallmark papers. These three papers, published by Hans Strachman and followed by Lise Meitner, Otto Frisch, and Otto Frisch alone, were hallmark papers in the history of nuclear fission. So in the meantime, the Paris and the New York teams, the Paris team led by Juliet's and the New York team led by Enrico Fermi, they both found that neutrons do come out from split uranium atoms. So this was the thought envisaged by Leo Szilard earlier. So then, of course, a chain reaction was possible, because if neutrons are coming out, that may further induce the fission reaction. And the only thing is, the basic nuclear physics is now understood, and the people has to begin how to do proceed further with understanding the chain reaction. So over 3 years later, beneath the bleachers of the football stadium at the University of Chicago, Fermi led a team of physicists who released the first chain reaction. So I just want to give account of Compton, who was the head in charge of physics division at that time. Rather than me narrating this, I just wanted to play an audio clip of Compton.
The balcony at one end of the room. On the balcony, a dozen scientists were watching the instruments and handling the controls. Across the room was a large cubical pile of graphite and uranium blocks, in which we hoped the atomic chain reaction would develop. Inserted into openings in this pile of blocks were control and safety rods. After a few preliminary tests, Fermi gave the order to withdraw the control rod another foot. We knew that that was going to be the real test. The Geiger counters registering the neutrons from the reactor began to click faster and faster till their sound became a rattle. The reaction grew until there might be danger from the radiation up on the platform where we were standing. Throwing the safety rods came Fermi's order. The rattle of the counters fell to a slow series of clicks. For the first time, atomic power had been released. It had been controlled and stopped.
So that was the voice of Arthur Compton, who was the head in charge of physics division at that time. There were people around that experiment were very happy and delighted. And this is the first reactor, a secretive reactor placed or designed underneath a football ground, code named as the CP1 reactor. And the room number was 34. You could search in the net to learn more about it. And this is called a Chicago pile, and there were graphite and uranium blocks, and the control rods were inserted, and it was being observed by the scientists from the other building or balcony. So they made history by controlling the reaction, and Fermi was congratulated by his team with the Italian wine, and the rest is history. So I just come to the last slide of my presentation, that these two reactions has made greater consequences to the mankind. In the first reaction, this is the induced fission reaction, where neutrons are allowed to bombard on uranium, resulting in fragments like barium, krypton, or the other fragments, along with the emission of a couple of neutrons and with a tremendous amount of energy. So the people behind the discovery of nuclear fission are Hahn, Strachman, Lise Meitner, Frisch, Niels Bohr, and Wheeler. So I have given the glimpses in the point of view of an experimentalist, but there were tremendous theoretical support put forth by Niels Bohr and Wheeler in understanding the fission process. And apart from this induced fission process, after some decades, two Russians named Flerov and Petersak, they have reported the spontaneous disintegration of heavy radioactive nucleus into two fragments emitting a couple of neutrons along with energy. So this process is relatively rare process than induced fission process, and these stalwarts has contributed to the mankind a lot. So with these words, I end my presentation and I extend my sincere thanks to all the participants who listened to this presentation. We could see more information in this reference. So most of the personal accounts I have taken it from this AAP, American Institute of Physics website, where they have historical information related to different discoveries. Thank you very much.